Good afternoon, everyone, and welcome on the ISQG YouTube channel. My name is Davide De Biasio, and I am a member of the Outreach Activity Team. Today, I'll have the pleasure of interviewing Alessandra Gnecchi, who's a researcher at the Italian National Institute for Nuclear Physics in Padova. Hi, Alessandra.
Hi, Davide. Thank you very much for this opportunity. It's very nice to be here with you.
Thank you for being here. Thank you for having accepted my invitation. Now, Alessandra, would you like to tell us something about yourself, about your research interest, or about all the things you do within the context of gravity, string theory, black holes, and so on?
Absolutely. I am, as you said, a researcher at the Italian Institute for Nuclear Physics. It's a general institute that covers high energy theoretical and experimental physics. Currently, I am in the Padova division of this institute, and I just moved here since last year. And I'm very happy to be back in Italy, let's say. That's where I started my career with my PhD 10 years ago. And I've been always fascinated in my research in the problems related to gravity. Gravity somehow is the force we understand better in some regions and worse in some others. And that's, I think, what a physicist needs to get excited. And so in these years, I've tried to work on some theories that tries to give meaning to what is gravity at various energies, pushing it at its highest possible energies, smallest possible scales, and many interesting things come out. And it's a wonderful theoretical ground to study. And it's been an exciting journey, and I'm looking forward to more years, many more years of research.
Well, thank you very much for this nice introduction. You mentioned a lot of interesting things, and concerning interesting things within the context of gravity, and in particular, among your research interests, black holes. Black holes are among the things that interest people the most, even from outside academia, right? They are super popular, but somehow people never take the time to really understand what black holes are, right? So can you please tell us something about what black holes are within the context of general relativity, and maybe then we can push it further if we like. But let's start from the first step, right? Can you tell us something about black holes?
First of all, that's correct. Black holes are some of the most exciting topics, both for a young student as well as an experienced researcher. That's what caught my attention when I decided how to start my research during my PhD, even my undergraduates. I really wanted to understand what these black holes are. And where do we start? Probably we can start with stars, right? Black holes have relevance in our universe. We believe they are the end point of the collapse of some stars that exist in our universe. And from the theoretical point of view, we explain them because if we believe in general relativity, which is the theory that's been so powerful in reproducing gravitational interactions in large scales in our universe, then we need to accept that general relativity predicts that there are objects that behave as black holes. The first solution given by Schwarzschild at the beginning of 1900s is the classical prototype of a black hole. It's a description of spacetime and how spacetime is curved in the presence of an object whose mass is distributed in such a way that it causes the light to never be able to escape. It curves the light cone of particles. What it means that it's a region of space that's surrounded by a sphere, its horizon, from where we cannot perceive anything. We can never detect something that comes from this region. oxygen. So it appears black because we do not detect light. And because of the following studies, these weird solutions people didn't believe in turned out to be actually a natural endpoint for collapse of matter. That's what the singularity theorems of Penrose was proving. So we had physically an explanation for why do we have to consider this kind of space-time structure. And slowly, we began, both from a theoretical point of view and from an experimental point of view, we began to believe in these objects. And so we started to be like, oh, there must be some stars that whose conditions of mass and density are such that maybe at some point no other repulsion is enough to prevent the final collapse. And only a few years ago, after a whole century and more, we had the proof that black holes exist with the detection of gravitational waves caused by black hole mergers. So yes, it's the universe who's telling us that we need to care about black holes.
So if I understand correctly, your argument, black holes are supposed to be objects, like, would you agree in calling them space-time configurations sourced by something?
Absolutely, that's what a solution of Einstein's equation is.
Perfect. So black holes appear when matter is packed, a given amount of matter is packed, or energy in general is packed in a small enough region so that nothing can escape, not even light, no signal, nothing. So for an outside observer, like outside the black hole, right, literally nothing is happening there, in the sense that no information can come out, right? This is the kind of picture you have in mind.
Yes, classically, that's what the study of the space-time structure tells us.
Perfect, perfect. So here we are in the regime described by general relativity, which, as you said before, is a super powerful theory describing a lot about a universe. But we know it is not enough. That's the whole point of this society, right? We are on the YouTube channel of the International Society for Quantum Gravity, right? So
exactly.
Not be enough. So before going into topics like supergravity or things like that, which might lead us towards a more fundamental theory of gravity, can you please tell us something about maybe where this classical description of black holes appears to break down? Like, does it present any problem whatsoever? Because one needs a reason to go beyond this classical description, which we made pictures of and found gravitational waves coming from mergers and stuff, as you mentioned. So is there any problem with the classical description?
Well, somehow it's funny you asked. It's what theorists do usually is they cook up a model where they can solve equation easily. And this model is the model where we derive the black hole solution. We put this distribution of energies, mass, this big mass in the vacuum, and then we see that this vacuum is curved to build this black hole configuration of spacetime. However, as we said, if these solutions appear in our universe, then there's not really a vacuum. Then we need, if we want to describe black holes in the real world, we need to take into account that the real world is made out of quantum matter. Parallel to the development of general relativity, we saw the development of quantum field theory that describes all the other fundamental interactions, telling us matter is fundamentally quantum. And so there must be a way to describe quantum matter in a curved spacetime. And that was the natural next step of the study of black holes, for example. And that's where the great figures of Hawking, but at the same time, Bekenstein, Carter, Bourdin were the ones who tried to describe and found the way to describe quantum matter in presence of black hole. So this is what we call the semi-classical descriptions of black holes. We take the solution and then we say, oh, wait a second, these solutions are in a vacuum, but we know the vacuum is really a quantum vacuum. It's a vacuum that can pair produce particles like the electrons we see and all the other quantum matter. What happens when these black holes is surrounded by quantum fields? And so what happened is that actually in these regimes, it looks like the black hole is essentially not really black. It's a thermodynamic system that has a finite temperature. So it emits what now we call Hawking radiation, who was the one that actually computed the temperature of these thermodynamic semi-classical state. And that's where the big questions that we're still working on started, because this thermodynamic system had associated temperature and a corresponding entropy. And a state that has entropy in statistical mechanics is sometimes understood as a macroscopic configuration of a statistical distribution of microstates. The problem with black holes is that having an entropy means these black holes have probably a configuration that corresponds to a certain gravity microstate. There's no way to describe a microstate from the point of view of general relativity. And so that's where we want to go beyond, and that's where we need a new theory that tells us what do we really mean by black hole entropy.
Well, I think this is extremely clear and points in various directions. This is the whole problem of quantum gravity appearing in our discussion, right? Because in order to describe this microstate, one would eventually need some quantum description of gravity, of spacetime in the end, right? This is the kind of thing you're pointing at.
Yes, because the reason why we need to go beyond the general relativity is that in general relativity, there's a uniqueness theorem. There's a no-hair theorem, sorry. It tells us that whatever state solution of the classical Einstein's equation we can derive with the same mass and conserved charges of the black hole is just the black hole. Mm-hmm. So we cannot find slightly different states that have the same macroscopic properties that behave like the black hole. That would be the microstate. So somehow there's just one state in general relativity that actually behave like the black hole. And so the entropy of a single state is 0. So there's no way in GR we can make sense of these microstates. We need to somehow break the assumptions of the no-hair theorem, and so either go in higher dimensions or include some non-local fields, or just a new theory that also describes gravity at the quantum level, where these microstates may have their own characterization.
Well, I would say that problems involving black holes were one of the main sources, right, of quantum gravity reasoning, and in the end from which quantum gravity approach is developed, right? And in a sense, a natural way of extending, and I'm asking you because I know you're an expert on this subject, but a natural way of extending general relativity is supergravity, right? So before going into supergravity, I guess that a brief discussion of supersymmetry might be needed. What do you think about it?
Yes. It's another interesting development, because although we're talking about theories of gravity and how to extend general relativity, it's interesting that these ideas and these developments were coming also from the attempts of physicists and theoretical physicists to unify the other fundamental interactions that we already know are quantized. We knew gauge theories that describe the matter in the standard model, and in trying to understand better how we can describe fundamental interactions, we knew that there were not many other ways we could build a theory of interacting particles. And so after the gauge interactions were understood and we built the standard model, there were attempts at unifying theories under a common either symmetry group or just generalized symmetry. And the one way to extend the structure was to go towards theories that presented supersymmetry. And it somehow emerged from various groups, this idea that we could find a a new theory where each particle had a super partner, with the fundamental idea being that the two partners were linked by being a fermion and a boson, or a boson and a fermion. So a symmetry that, differently from the previously known gauge symmetries, would link together particles of half integer spin with particles of integer spin. And that is somehow the core of the supersymmetry action, is to transform a boson into a fermion or a fermion into a boson.
And in this sense, just to make it clear, even for people that might have heard this for the first time from you now, right? You mentioned bosons and fermions, which are the two big families of particles we have. And what you're saying, if I understand correctly, and please correct me if I'm wrong, you're saying that starting from a theory of particle physics, namely the standard model, and a possible idea, possible development is to enlarge the kind of symmetries we have, add the new symmetries, and in particular, a symmetry that maps bosons into fermions and fermions into bosons, like associating to each particle a super partner, right? Like to
yes.
the electron, the Z-electron, or stuff like that, or to the gauge bosons, some other fermionic partners, and so on and so forth, right?
Gauginos, and yes. It's and somehow it's the only way. Like, we can extend the symmetries of the standard model, like by going to higher group symmetries, larger group symmetries. Yes. But if we want to add a completely new action of this symmetry, then it's proven that the only other possible way is to go to a symmetry that changes the spin, the integer spin in alpha integer spin, and vice versa. And this is very well known from the algebraic point of view, but from the physics point of view, if a symmetry like that is a symmetry of nature, it means that whatever particle we have discovered in the standard model, then these particles must have an associated corresponding partner of a corresponding alpha integer or integer spin, and that's where the problem for phenomenology started, meaning we have not detected any of these particles. This means, and it's possible if there is a mechanism that breaks this supersymmetry at some energy, and so these super partners, which are other fundamental particles, are actually so high in energy that we have not discovered them yet. And so there were a lot of hopes that the LHC in its run not only would discover the Higgs particle, which it did, so it fulfilled its job. It was a fantastic discovery for the standard model physics. But in addition to that, it could have been that we could have reached energies such that these particles were discovered. We haven't seen them yet, and so it remains an open question to see at what energy supersymmetry is broken, if we assume it's a symmetry of nature. And I think that this is where let's say, theories of standard model physics and extensions of the standard model now merge towards theories of quantum gravity. Because if from the point of view of standard models, maybe for reasons of energy scales and the hierarchy problems, one could still be motivated to try and propose a theory that has supersymmetry at a certain scale. It's when we look at quantum gravity that it becomes, we're almost forced to introduce the supersymmetry. So if we want a theory that describes also gravity at the quantum level, some of the most important theories we work with today, they somehow require supersymmetry to be a symmetry of nature. So it's given that at some point supersymmetry will be restored. We may never be able to see it at accelerator energies, but it's there, and in theoretical physics, we sometimes take it for granted.
Yes, clearly, at least part of the people working, a portion of the community working on quantum gravity, in particular those working in string theory and superstring theories. I mean, the word super comes from there, kind of work in a supersymmetric context. Clearly, just to make it clear for our audience, the whole point of this project is to explore the various perspectives on quantum gravity. And so some assumptions must be made along the way, right?
Exactly.
And in this sense that Alessandra is making clear, the assumptions we're going to make in starting from supersymmetry and leaving open the question whether it's actually realized or not, and so on and so forth. And within the context of this kind of perspective, now trying to make the step that goes beyond the supersymmetry, right? Because this is not the whole story. Before I mentioned supergravity, and I wanted to ask you about supergravity. So what's the deal with supergravity? Is it just supersymmetry applied to gravity, to general relativity? Is it something more? How does that work?
It's a natural extension of the question if we push this supersymmetry symmetry into the physics that we know, how does these act in the gravitational sector? And moreover, it's a way of having a local realization of the supersymmetry action. If you introduce this, then you automatically are required to have a spin 3-half particle in your theory. And the spin 3-half particle is a mixture of fermion, like an electron, and a vector, like the photon. It contains both in some ways. And it's needed once we have this local action of supersymmetry. Basically, that defines the theory of supergravity. And what's important is that this gravitino field is called gravitino because it's the superpartner of the graviton. The graviton being the field that describes the field of gravity, the gravitational interaction. And that's where we cannot escape anymore from a theory that is an effective theory of gravity. So we want to extend general relativity that we know works in our universe to more fundamental theories of particles. And we want to extend it theoretically to understand the properties of this theory and possibly making prediction already at energies that we understand. So that's why we say it's supergravity is a low energy effective theory of gravity. We could see a supergravity particle in our world, maybe with the couplings that are very, very small. And so maybe part of dark matter could be made of super partners of the standard model partners that somehow are weakly coupled for some dynamical reason. So it's somehow a natural extension, the easiest step we can think of by going outside of the standard model to a theory of interactions that also include a gravitational field. So whenever we talk about graviton, we are starting to say that we recognize there is a fundamental particle associated to gravity that mediates a field that mediates the gravity at the semi-classical level, and that is the graviton. It's what gives rise to a metric that can be curved. If there's no graviton, then whatever spacetime we have given, we can study matter on this spacetime, we can study scattering of electrons on this spacetime, but we will never modify the spacetime. If we start with flat space, we'll be always studying a theory and interactions in flat space. If we start with a sphere, we'll always study a theory of matter on a sphere. But if in our theory we start taking into account a graviton that interacts with all the other particles and couples to the other particles, then it could be that in our theory we describe also curved spacetime. So that's how we can study also black holes and other again curved spacetimes. So supergravity somehow comes in when we want to add gravity to the game of fundamental interactions at the lowest level. Yes,
in this starting from this supersymmetry proposal and then extending it to supergravity, and so having this locally when you mentioned local supersymmetry, just to make it clear, and once more, correct me if I'm wrong, the idea is not only to apply your symmetry at each point in the same way, but at each space-time point in a different way as you like. This is the idea of a local symmetry or a gauge symmetry, as you mentioned before, right? So assuming to work within this within this proposal of supersymmetry and supergravity and so on and so forth. Now, going back to a more phenomenological question, right? And going back from where we started, what happens to black holes within the context of supergravity? Can we describe black holes? Do we learn something more? Do new features appear? How do super gravitational black holes work?
Yes, so this is where I think you can start seeing that supergravity is a very powerful framework, because first of all, whatever black hole solution you have in GR, then this is a solution of the supergravity theory too. Like you can extend the theory, but still look at simple configurations, and you recover the black hole solutions we know, like the Schwarzschild we mentioned before, or the charged version of a black hole, which is so-called Reissner-Nostrum, from the people that discovered it, that I'm pretty sure I did not pronounce correctly. So then you can look at what is the role of these solutions in this theory. So let's look at these black holes. Now, can I modify them a little bit? Are they a class of solutions? What happens? And in supergravity, you have the freedom, and somehow we're now taking the approach of the theorist. We are after understanding the nature of some curved spacetime, and we want to play with it a little bit to understand better how it works. And so let's play with this added symmetry in a theory that now we are free to look at standard model particles, but add more standard model particles, or let's say more particles similar to electrons. Let's say let's just add new electrons with different couplings, their spin 1/2. We can even add scalars. They come naturally in this theory. And so,
pardon if I jump in, but just to make clear the kind of approach, because it might sound weird to someone outside of the field. This sounds like what engineers do when they do stress tests, right? We take our framework and we start testing it and stressing it and seeing what happens under different conditions and with different matter contents. And so is this the kind of idea you're pursuing?
Yes.
Okay.
It is stressful in some ways, not only more for the engineers in the question than for the solutions themselves. Sorry. It's exactly trying to understand how well you understand the system. You have certain intuitions, you know, that the system is curved, the system has a certain temperature, and then you're like, okay, what if I modify? What if I add more matter content? What if I was free of considering any kind of interaction? And so what we see is that, for example, in the case of Reissner-Nostrum solutions, if you are in a supersymmetric theory, then you can have a particular configuration where you can send the temperature of the black hole to 0. Sending the temperature of a system to 0 is not something natural from the point of view of physical systems. It's weird things happen when temperature goes to 0. Like I mean, it's a theorem, right, of statistics. You cannot set T to 0 to a physical system exactly 0. You always go to 1 Kelvin or 2 Kelvin, and it's really difficult. So
pardon, the so-called absolute 0 one might
exactly
heard in high school or something like that, right?
And that's where the limit where, for example, interesting things happen, because in that limit, well, then your curved spacetime somehow becomes a sort of universal geometry that as a 0 temperature, it stops radiating. There's no more Hawking radiation, and it's a stable space-time. It's so stable that somehow it's protected by supersymmetry itself. It preserves the supersymmetry. It's compatible with the symmetry. There's something that leaves the space-time invariant. We can act with our supersymmetry. We can change something in our configuration, but still some part of this action is actually leaving the configuration invariant. And this is important for physicists, because it means that we're really looking at something stable. And these are the so-called BPS black holes that are very important for people that work with supergravity and that work with string theory. And in fact, I would say that one of the major results of string theory was precisely understand that these black holes, that even though they have zero temperature, they do have some finite entropy. When we send the temperature to zero, we don't send the entropy to zero. So there's still some microstructure to these systems. And string theory was able to provide the microstates for this system. So we've enlarged our original theory. We've gone beyond the GR, we've gone to supergravity. Supergravity is a low energy theory that describes some states that we still see at low energies, like black holes. Mm-hmm. But if we can even do more, we can even say, okay, supergravity is just an effective theory of a bigger fundamental theory, which is string theory. And then we connect the two by saying, okay, in the bigger theory, I recognize what the black hole microstates are, and they appear as black holes in supergravity.
So you anticipated my follow-up question in the sense that I was about to ask you how supergravity connects to superstring theory in a sense. But as you said, if I understand correctly, some kind of large scale or low energy limit of the kind of dynamics you have in superstring theories, which appears to be a more fundamental theory with respect to supergravity within this framework and context at least. Right.
Yes, and we can say something more because it's a very important point. It's supergravity is a theory that has developed by itself. It's a consistent theory at low energies that describes, as we said, some local action of supersymmetry. It can include standard model particles and many more. So from a phenomenological point of view, one could look at supergravity in the universe. However, it's also very important that it's a framework where we can take my favorite theory of quantum gravity, in this case, superstring theory. And superstring theory is not automatically a theory which gives a geometric spacetime as a prediction. In some regimes, with certain assumptions, we demonstrate that string theory has as a solution spacetimes which contain black holes of a certain curvature in certain geometries. And so it's important that we have a supergravity description that provides the correct description at low energies for string theory. Mm-hmm. So it's the framework where if we want to deal with geometric realization of string theory, mm-hmm. we need to be able to compute things in supergravity.
Before going back to black holes in supergravity, because I'll ask you something more about this temperature and so on and so forth. Let me please focus a bit more on an interesting thing you mentioned, namely the fact that superstring theory. So you said that supergravity comes as some kind of low energy limit of superstring theory taken as some fundamental theory. But in some sense, you also said that superstring theory can give rise to non-geometric spacetimes. Can you elaborate a bit more on this kind of idea? Because I guess that since we describe the spacetime as a geometric object in general relativity, the idea that it might be non-geometric within the context of a theory of quantum gravity might come as a surprise. So what's the deal with it?
It's at the fundamental explanation of how you match the black hole microstates with states in string theory. So basically, string theory is a theory that has certain parameters. And among these parameters, there is the possibility of tuning the gravitational interaction of your fundamental constituents. Fundamental constituents in string theory can be fundamental strings or higher dimensional objects, the so-called D-branes, if we're in string theory, or in 11 dimensions, these are M-branes, but let's say extended objects. And there is a regime that is interesting because we can describe these extended objects and strings on it and associated gauge fields, which are predicted by the quantum theory of the string worldsheet. And these are somehow have a description in terms of superconformal field theories, and in various dimensions with various supersymmetries. This is a description of these objects, extended objects, at the zero or small gravitational couplings. These fields and these configurations do not back react, we say, in space-time, and do not curve it. So we have the possibility of using string theory to study very complicated systems, because these super conformal field theories are certain kind of quantum field theories with conformal symmetries, which in various dimensions may not even have a Lagrangian description. The only way to tackle this is really looking at the stringy realization and looking at their symmetry groups, at their fixed points, and it's a very interesting and fruitful part of research in theoretical physics. However, there is a possibility, if we look at the states in these theories that preserve supersymmetry, the so-called BPS states, then there's a possibility to recognize that if we start moving regimes from these, let's say, zero gravity coupling regime to a strong gravity regime, some of these states, we can still pinpoint them and we can still keep track of them. And if we move to a finite or strong gravity coupling, strong gravity coupling means that things are really, really acting on your space and things are becoming heavy. It's like we're cranking up our weight. And if we crank up our weight, then ourselves are able to attract stuff from, because we ourselves become a black hole. And so let's say very heavy. And so we assume that there is a region where space-time become curved. At the same time, in this region, if we are still at low energy, we have a geometric description. And because of supersymmetry, we are able to say that while we tune the parameter that takes us from small gravity or zero gravity to strong gravity, so geometry, curved space-time realization, in this interpolation, there's certain states that we can keep somehow under control. And these states are the ones that once we go to a curved spacetime, they are giving us the black hole.
Okay.
When I say only this subset of state, it's because the moment we turn on gravity, in general, we go out of a region or a regime where we can even make any computation with these branes and strings that we had before. We really are messing up our system. We're going to strong coupling in certain sense, we're back reacting. This is really, really messy. And we, in principle, would not be able to do anything. But because there is what we call a sector, that it's preserved by supersymmetry, then we can keep looking at it and then go to a regime where this sector is still there, but we have a geometric curved spacetime.
So just to sum up what you just said and see whether I understood it properly. First of all, when you talk about tuning the strength of gravity, you actually mean something like, as people listening to us, if someone survived up to this point, then it's like the strength of fundamental interactions is usually controlled by some constants, right? For instance, Newton's constant, everyone has seen it in high school studying Newtonian gravity, right?
Exactly.
Weak gravity corresponds to a very small value of the Newton constant, and strong gravity corresponds to a very big value of Newton's constant, and this can be roughly tuned from a small to a large value, right?
Exactly. That's what we mean.
And in the weak gravity regime, when Newton's constant is really small, things are easy to be dealt with, or at least feasibly solved, and so on and so forth. And then you can keep track of how things transform when you tune up Newton's constant, and still you're able to say something about gravity when it's strongly coupled and so on and so forth, even though starting from there would have been too hard because gravity would have messed up everything. Is it more or less the picture you have in mind?
Yes, yes. And I say strong gravity still with the idea that we are at low energies. And so somehow there is a back reaction of your states on the space-time, but there's no strong quantum gravity effects, let's say.
Yeah.
So we're still going in a low energy regime where there's like a background that's however curved. The idea is that in string theory we can really decide what we are describing, and as I was saying, there's a regime where its fundamental constituents are filling the gauge fields exactly like our standard model particles interact when they're smashed at the accelerators. So they're sensitive to their gauge charges, but they're not really attracted gravitationally. Exactly like when we scatter particle at the accelerators, their mass is so small that there's any effect we see is not given due to gravitational interaction. And so
it's somehow, right?
Exactly. It's not part of the game. So we can take strings, fundamental degrees of freedom, fundamental strings and branes of various dimensions, and see what happens when they interact, but their mass is too, or their tension is too small to feel the gravitational attraction in a way that they do curve the space-time. That's the regime I was talking about.
Okay, thank you. So this allows you to control, like one of the reasons for which this whole supersymmetry and then supergravity game comes out to be quite appealing is precisely the control it gives you over computations in particular regimes, right? It allows you to draw some conclusions on some specific regimes and so on and so forth, right? For instance, computing the entropy of a black hole in, as you said before, and so on and so forth. And now, within this context, if I may move to, because I'd like to talk to you for 5 hours, but no, I don't want to.
You're right.
Take advantage of your kindness, right? But moving to
mostly the people listening.
No, I think that if they got to this point, as I said before, they are truly interested and they'll go until the end. So it's more not to abuse of your patience, but going to more recent developments, right? Within the context of superstring theory, within the context of supergravity and so on, a proposal for solving the so-called, I would call it information problem, not paradox, because if there's a solution, strictly speaking, that would not be a problem. We mentioned it a few times on this channel, so we can go quick on this, but a new proposal for solving this kind of problem with black holes, evaporation and radiation and so on appeared, right? Would you like to say something about it, right? Because I think yes. I heard it from you when I first heard it, so this would be
yes. As I say, like it's a very exciting field of research because there's still like interesting aspects to analyze and things are happening fast in our field. And it was a pleasure a few years ago to discover some new results and follow them a little bit. So what's happening recently is that we've we started looking at quantum fields in the presence of a black hole background from more perspective, and a new player entered the game, which was entanglement of quantum fields. Because in the recent years, there's been a lot of development in building entanglement for in quantum field theory, understanding entanglement of sub-regions of space with the rest of the system. And we understood that we probably need to look at the black hole, semi-classical black holes, also from that point of view. So what is the structure of entanglement between the region of spacetimes and the rest of the interior and the outside of the black hole, some subregions of our spacetime with other regions, and there's been a lot of development in this direction that naturally also touch the problem of black hole evaporation, because in the if you said you've talked in this channel a lot about already information problem, we can just remind.
Yes, if you want to quickly go over it just to refresh it, but yeah.
Just probably to point to the fact that we understand the evaporation, the emission of radiation from a black hole as a sort of pair production near the horizon. The quantum vacuum produces particles that, because of the structure of the horizon, are allowed to somehow escape. One particle escapes, the other particle falls back into the horizon. And this creates an entanglement, because the pair production of particles from the vacuum creates a particle that is entangled, maximally entangled with its partner. And that's where naturally you're led to address the problem of entanglement. And not only the entanglement, but the evolution of entanglement and the evolution of the black hole itself. We want to describe black hole physics and black hole in dynamics in a semi-classical way. So we want to say, oh, this is my black hole, it starts evaporating. At the end of evaporation, I have collected all the black hole in the form of radiation. Well, if I'm a good physicist, this must happen in a unitary theory, because we need to preserve probabilities of the original particles that collapsing produce the black hole. So this seems something trivial to state, but very difficult to realize in a consistent way in the theories we have at hand. And so recently, a big development was actually a quantitative prediction that was telling us, listen, there is a way to make sense of this evolution and a unitary description of evaporation. And the reason is that what people discovered is the presence of subtle points of the quantum gravity path integral that we had not thought about before, that comes from a particular formula, and probably we should say something about how this formula came out, that is motivated more studies and more discussions about, do we really understand the gravitational path integral? Are we ready to go beyond what we thought was the semi-classical description, and what can we consider beyond the usual Hawking calculations? And what I wanted to say is that a lot of these developments came from a new approach to gravity. And by new, I mean 25 years old, which is holography. So what another big development that came from string theory was another quantitative prediction of gravity as a conformal field theory. So gravity at the quantum level has a holographic nature. It is it needs to be addressed as a theory in one dimension less, at the boundary of an appropriately curved spacetime. So this paradigm that has made huge developments has told us that somehow we can make the black hole and let's say a space-time emerge from some boundary theory. And the final quest, I think, in people interested in understanding what is the quantum nature of space time, is to understand this emergence. How do we make sense of space and time and black hole evolution and entanglement of fields in a holographic way? From the point of holography, these new solutions of the gravity quantum path integral arise as somehow some extremization points of a functional that is well defined in a holographic way. And this is what goes beyond the usual calculation that we only addressed from the point of view of just our theory, our action, our bulk perspective. We need to push ourselves to the boundary and then change the paradigm, and then go back to the bulk and say, oh, that's what we were forgetting. And that's where people starting to look at Euclidean solutions, wormhole solutions. And there's a very interesting field of research now devoted to understand what is the role of these solutions we somehow disregarded, but they seem to, be needed for our description of black hole evolution at the quantum level.
So summing this up, so we start, and stop me in case I derail, but we start from this information problem / paradox, as you like, namely black holes appear to have a temperature, they appear to evaporate, namely if you emit radiation, you need to shrink or something. And this appears to clash with some basic properties of quantum mechanics, unitarity, probabilities being conserved and summing up to 1, and so on and so forth. We've discussed this. Now, you mentioned quantum gravity path integrals, namely an approach to quantum mechanics in which our systems appear to be given at a quantum level by superpositions on different possible configurations, right? We already discussed this, so going quick on it, the upshot, if I understood correctly, is that to describe within this context the evaporation of a black hole, you really need some quantum gravitational corrections that come from considering other solutions that appear in the path integral and give non-trivial contributions to, you mentioned saddle points, right?
Yes. There's still somehow, you don't need the action of the quantum theory of gravity, because that may not even be known as an action or Lagrangian level. You need your theory, but you need to consider new saddle points. You need to go beyond your one single spacetime, and it's still, let's say, there's still research going on in this direction. That is so things. We may say something that needs to be understood better. I'm pretty sure there's someone who understands it already better. but yes, there's this interplay, I would say, between development of certain interesting ideas in about entanglement and quantum information that are built at the boundary, and then these efforts, which is a fantastic, I think, effort of people trying to understand quantum gravity, which is how to extrapolate this behavior at the boundary with the idea that this is just the boundary of a gravitational bulk. And so there's somehow as I say, this emergence of properties in the causal structure of the quantum spacetime that can be understood in these from this holographic point of view. And how is this emerging, and to what extent we understand it, to what extent we need a new dictionary, is probably what is going to teach us more about the fundamental origins of gravity and quantum information at the level of black hole dynamics.
Well, with this, I would say, optimistic perspective, in the sense that we somehow have a context in which we can propose a way to go beyond the problem of at least of the information information being destroyed by black holes, and have some perspective which might give us a fundamental understanding of space-time. And being at the boundary of current research, because we are discussing stuff that happened, which is still partially solved, partially work in progress, which is really, but this is part of this initiative. Namely, we want to give people a perspective on what's actually happening in the field of quantum gravity, right, from various in various corners, I would say, of the discussion. Let me move, if I may, to a more personal perspective, right? You told me why, to a more personal question in conclusion of this nice interview, for which I thank you again, by the way. You told me already that you went into gravity and then quantum gravity because you were interested in black holes. So this would have been my closing question. So I'll push it a bit back, I'll do one step back and ask you, why physics in the first place?
This is very much a cliche answer, but I wasn't third year of elementary school, and I read a book about the life of Marie Curie.
No, this is super important.
For real, for real. I was passionate that she was a woman in a field of men, and there was a role model. I was like, okay, someone can do it. I can do what I want, and I was fascinated that she was running around with her car and an X-ray machine to the camps during Second World War, trying to do X-rays to the military. So there was a bit of a sort of active perspective of it, and of course, I mean, the fascinating world of understanding the fundamental of our universe has always been fascinating. And sorry, I say all this cliche part because then I also say I had never done enough physics to understand what it really meant to do physics until it was too late to change, right? So it's the problem when you follow your passion, then you understand what your passion is. And no, I have been very privileged in being able to study physics and continue with a career in physics. I've had support from so many people, and I've been lucky enough. But it was a passion, right? It's the curiosity. I think that many of us are curious, and some of us are coming from an environment where something tells them, I can do it. And I think it's very important because it opens your mind on questioning so many things in the world, and then everything becomes a physics system for you, and it gets fascinating.
It's the rabbit hole, right?
Yes.
In a sense, thank you, because I asked you about your personal experience, and you brought up many important issues, which I'm happy we mentioned today: role models, representation, the importance of having someone to get inspired from. Like, I'm sure you'll be someone's Marie Curie one day, but so the reason for which someone went into physics, I'm not qualifying this statement. It might be a bad thing or a good thing.
Yes, no. I was gonna say I have some nephew,
also
and
someone's problems in right in having chosen physics. But except for this, I want to again thank you for having me here today, and I'm sure this interview will inspire many and tell many and be a source of many interesting insights about what's happening in quantum gravity. So thank you very much, Alessandra.
Davide, thanks so much to you and to the society for having these series. I think it's very important because, as you say, there's a big part of physics that needs to be communicated, and it's thank you for doing this. It was really a pleasure.
Thank you again, and see you soon.
See you soon.